IPS Signatures, Signature Engines, Part 1. Well, we've come to that point in this series. When I say that point, I mean, well, let me explain. Just about every series that I do, whether it be in Cisco technology and Microsoft technology, you always get to that section. And I always call it the taking your lima bean section because it's the stuff that you have to know, you have to understand it, but it's just not fun. Well, it's not that this won't be fun. Okay, it won't, but it's just the section where it's good information, you got to know it, but there's no action involved. We're not really going to be doing too much configuration. So that concept in this series is called signature engines. It is absolutely important because we're going to be discussing the engines or all of the engines that run your IPS sensor. We're going to define a signature engine and its purpose, talk about what it's all about. Then the rest of this series is going to be talking about all the signature engines that exist inside of your IPS sensor. Now, there's a lot of them, and there's a lot to them. So I'm not going to discuss all of them in just one sitting. I wouldn't want to kill you. What I plan on doing with this first nugget is I'm going to go through atomic, flood, meta, and normalizer. Then in part 2 of this series, we'll go through the service, state, string sweep, traffic, and Trojan, and AIC. All these different signature engine types, talking about the use of each one of them, how they can apply, and what sort of traffic they inspect. So we've talked about signatures and alerts, and now we're bringing up this topic of a signature engine. So we have to ask that question first. What is a signature engine? Well, I put the definition as simply as I could. It's a component of the IPS sensor that manages a smaller subset of signatures. See, it's almost like a paradigm shift. When you look at the sensor, you see a box, you see a piece of hardware sitting there, and you think, oh, there's a processor, there's memory, and so on that runs. It's just a little mini computer is really all it is. But you have to kind of change that paradigm a little bit. And instead of thinking it as just a box, you can think of it as a box that contains a bunch of small little engines, like propellers, like you see on the screen. Think of a boat with like 12 or 15 propellers that are out there because there's these individual engines that manage their own little section of signatures. For example, we have an engine that will manage just the signatures that deal with reconnaissance attacks, meaning people probing the network to get information. We have just a signature subset that deals with Trojans and the things that can get installed on a client PC and attack from the inside out. So all of these signatures are managed by these individual engines. Now, these engines have a typical set of parameters that they apply to all their signatures. That's the default set. But we have the ability to go into each and every signature and tune the signature and change what that engine applies it as. And this really helps us divide our IPS into a specific set of individual engines. And it also helps us see if we're starting to slow down, which engine is causing the slowdown? Are we getting a bunch of, Trojan attacks or reconnaissance attacks that are really cranking up the processor power that engine needs? So it really helps subdivide our one sensor into many. So here they are, the signature engines that our IPS sensor supports. Now, I'm not going to sit here on this one slide and tell you about each and every one of them, but sometimes just by looking at the name, you can get a good idea for what they do and what signatures each of these manage. And I guess before I go any further, I want to make sure I emphasize that. These engines each manage their own little signature group. You can almost think of it like some kind of weird Amway structure where you have the IPS sensor at the very top of this pyramid scheme, and it goes down and kind of delegates its responsibility to these signature engines, the atomic, the flood, the meta, and so on. And then each of these contain pieces that are their subordinates, and those are the individual signatures. So for example, under the atomic signature engine, you typically will find other signatures that make that up. So just to hit some of the high points, the atomic signature engine, we're going to talk about that one first, allows you to put the signatures into a category that match a single packet. Atomic signatures are the ones that say, I found a single packet, it's bad, sound the alarm. Flood signature engines are the ones that allow you to detect, for instance, a denial of service attack, a flood of data coming in, and all those signatures report to that. So as you go through these, you'll see each of them has their own specific purpose, and that's what we're going to do is go through that purposes one engine at a time. So here we go, starting off with the atomic signature engines that manage all the atomic signatures. These engines, as I mentioned just a moment ago, were the ones that trigger from a single packet. And there's really two atomic signature engines that exist. There's the atomic ARP signature engine that manages all the signatures that deal with the layer 2 ARP protocol. There's actually multiple signatures that deal with that. And then the bigger one, the atomic IP signature engine, deals with all the packets that deal with the IP protocol. It's pretty big, but they're focused around IP attacks that are contained in a single packet, or anomalies that are contained inside of a single packet. Okay, I've whisked over to our IPS sensor. I just want to show you an example of some of these atomic signatures. I'm going to go to the signature configuration right here. And this is right now listing all the signatures that are available, all 2,000 some signatures that are in here. Now, you can't really search by engine, but I don't know if you ever noticed when we were looking at these signatures in previous videos, we have kind of these breaks. You see like 1,000, 1,001, 2, 3, 4, 5, 6, 7, then 1,100, 11, da, 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 and down we go. You know, we get these breaks in the line up to 1,109, down to 1,200, and so on. You just keep kind of doing these big jumps. And what those jumps represent is you're jumping between signature engines. For example, I'm going to go ahead and just put ARP in here because atomic ARP is one of our signature engines. And there's all of our atomic ARPs. They're all of the 7,000 or 7,100 range, which kind of designates them as being lonesome. Now, this right here is, you can see LSARP, so it just matched the ARP in that word. It's not really part of that group. I'm going to jump under let's go under ARP source broadcast and click on edit. Now, this may be the first time you've seen this edit signature page. This is where you can get into the details of the signature. And as of right now, everything is set at the default. I know that because all of these green boxes are still green. If I were to modify something, I would click the green box and you can see it changes to red, letting me know I've tuned the signature. Remember the three types of signatures, the built-in, the tuned, and the custom. I'm just modifying one of the built-in signature here, and at that point, you can see the little red box. I'm going to change that back to the default and jump down here. Scroll down to the engine section and look at this. Engine is atomic ARP. So I can see what engine is managing this signature. Now the event action right here, right now, is just produce alert. And I can scroll down and first off you see specify type of ARP signature. This really is what differentiates all four of those signatures that are going through. You saw when I did that search for ARP, I had 4 signatures. They're all the different kinds of ARPs that are weird. You can see right here, this is the default. I'm going to change the type of ARP signature. As of right now, it's saying I will trigger this signature when the type of ARP signature is a source broadcast, meaning the source address in the ARP message is a broadcast, all 255, 255, 255, 255. Now, the way an ARP works is when you ARP, you're pretty much saying, hey, I am 10.1.5.1, and I need to find out who is, 5.9.2.1. It sends out a broadcast saying, hello, network, who are you? Now, it would be weird if you had an ARP that had a source address of a broadcast. That would be a type of attack. Trying to get that person to respond to a broadcast address so everybody gets it. Could be a denial of service. There's many ways that you can use that. But you can see there's 4 different types here. I have the source broadcast. The second one here is the destination is a broadcast. And this is another type of signature where somebody would be trying to send an ARP message to a broadcast, meaning the destination address is a broadcast to try and get everybody to respond and get all the MAC addresses on that network. Now you can see right here, same source and destination. That's where the source and destination addresses inside of the ARP message are the same. Now again, every single one of these things I'm talking about here is an oddity. It's weird. It shouldn't happen. That's why we have these signatures that match these things. They're known attack types. Right here, the source address is a multicast. So these are all things that should not happen, and I'm going to change these all back to the default and not modify that signature. But that's really what it differentiates those four signatures that you saw is really the type. Now, right here you see the specify request imbalance. If you change that, it's no or yes. The request imbalance means there's a larger amount of requests than there are responses. So that means you are starting to have requests shoot out there, but nobody is responding to those requests. Now, that may be a normal thing. I mean, maybe somebody pings for an address that doesn't exist. Well, the first thing that happens is your computer is going to send out an ARP message saying, "Hello, who is this address?" And at that point, when the address isn't there, nobody's going to respond. If we turn on request imbalance, you want to make sure that this number that you put in here is something you can see minimum 0, maximum 6,535 or 65,000, sorry. That needs to be a number large enough that it doesn't trigger false alarms. For example, if I had, we'll say, 500 requests for an address and no responses, I would consider that weird. That would be something that's going nuts trying to find an address, and there's just nobody out there with that address. There's no response coming back. I want to know about that, so that's when this signature will trigger. So that's what this, request imbalance does. And I'm not going to go in this kind of detail with every single signature because we would be here for, well, days. There's, every single signature has these tunable options like this. But and that's what you can see. As soon as I click that back to the default and change it back to green, it erases all of my changes and sets the signature back up to the way it was. But all of these signatures, and I'll click OK on this, each and every one is managed by that same engine. You can see the signature ID. They're all of the same genre. They're all managed by the Atomic ARP engine. Now let me show you a little easier way that you can find what signatures belong to what engine. So far I'm looking by signature name, but I'm going to change this dropdown and I'm going to select the engine that it belongs to. And voila, just like that you can see all the different engines that we have. The AIC, the Atomic ARP, Atomic IP. I mean all these different pieces, these are the ones that I talked about on that bullet list. Service string, sweep, Trojan, traffic. All these individual ones, and if I select Atomic ARP, that's where you can see just those four signatures I found by just querying for ARP. Now I'm going to change it over to Atomic IP, and you can see that there's, we'll say a few more engines, or a few more signatures I should say, that deal with the Atomic IP engine. Now we can just pick on one of these. Let's say I want to focus in on, we got some ICMP, echo reply. We dealt with that one in earlier nugget. Here we go. How about a TCP null packet? Something that deals with the TCP protocol. I'm going to bring that up in the edit screen and scooch it over. And in this signature, you can see the signature description and so on, and you can, of course, go to that database and find out all the specifics about it. But let's wait for that to come up on the screen. There we go. And you can see that this is focused in on the layer 4 protocol. I've got it all zoomed into the right area. It's producing an alert. Whenever I have a layer 4 protocol, and you can see the status is that it is not fragmented. And you can also adjust that to say it's fragmented. It is using TCP as its protocol type. And you can see this drop down, ICMP, other IP protocols, UDP, all of our options there. What flags is it focused on in the TCP packet? We can specify a certain window size, a certain TCP mask, and what the mask does is that allows us to zoom in and focus on just a specific type of TCP packet, like just the acknowledgement or just the SYN bit. I mean, all of these things allow us to focus in on this. Now, this signature that I popped up there, I can't even remember the name of it at this point, but it has its predefined settings for what it wants to zoom in on. You can see, the payload length, urgent pointer, all of these things are specified with a yay or nay. And down there you can see the destination port range that has been predefined, 1 through 1024. So it knows exactly what it's looking for in this setting. I'm tuning it, if you will, by making these user modifiable and changing these options. But that's a glance at the atomic IP segment. And you can see there's so many more signatures that fall under the atomic IP than the atomic ARP because right there, UDP bomb, SNORC. These are all different applications that are used to attack the network. And there's so many different things that deal with the IP protocol that they had to have a trillion signatures to handle it. So let's move on to the next signature engine, and that is the meta-signatures. Meta-signatures are unique in the sense that they are a engine designed to, let's see, what's the best way to put that? An engine designed to analyze multiple signatures firing rather than just one signature. Here's what I mean. In one of the previous videos, we did a UDP port scan. And you saw that when we did the UDP port scan, not just one signature fired, the one that triggered a UDP port scan, but it also noticed it said, hey, you're under a DHCP attack, you're under, there was like 3 or 4 different signatures that fired just by doing a UDP port scan. Well, the job of the meta signature is to analyze multiple signatures firing and go, this means something. All these signatures firing mean that XYZ is happening. For example, a good example of this is the NIMDA virus. When the NIMDA virus, or worm, came out, what it did was it actually triggered like 5 or 6 different signatures all at the same time on an IPS sensor. Well, the job of the meta engine is to put all those pieces together and realize, aha, this is not just a bunch of strangely firing signatures that just so happen to all fire it at the same time. Adding all these pieces up means that this is a kind of mother signature, if you will, that recognizes the NIMDA virus. So let me put it this way. The big difference from the meta engine from all other engines is all the other engines analyze events. They have individual signatures that analyze events happening on the network. The meta engines doesn't look at individual packets or events. It looks at signatures firing. It looks at, how many signatures fired, those 3 signatures. By combining those, do I get some parent signature that encompasses them all? I'm taking you back over to the IDS sensor and change the selected engine to the meta engine. And you can see just about all of these signatures underneath, well, I guess you could call them parent signatures, are all sweep descriptions, meaning it's typically sweeps of the network where multiple signatures are triggered and the meta engine goes, aha, I know what you're doing. For example, I've got red button that's just selected by default. I'm going to edit that one. And you can see when I go to edit this signature, and I scroll down a little bit, we are sitting in the, wait for that to refresh and come up, but we're sitting in the meta engine. And instead of having all these adjustable criteria, they have a component list. So what this is it's going to be a list, I clicked on that little pencil, a list of the sub-signatures that have to fire in order for this parent signature to fire, this red engine. You can see selected entries, we have these individual entries. I'm going to click on edit, and you can see that this entry key number 1 is actually signature 3306 sub-signature 0. And it's saying if that signature fires plus, hit the edit on sub-signature 2, plus 3308, plus, are you getting the picture? 3309. If all 3 of those signatures fire, aha, we have discovered the red button signature or parent intrusion. And I'm not too sure what red button exactly is, but it sure sounds serious. But that's an example of the meta signature. Next up in the list is the flood signatures, and this is a signature engine that triggers whenever you have a single host or network sending or receiving a flood of traffic, something out of the norm. So some individual host or some sub-network is getting just hammered. And you can see there's 2 types of these signatures that this engine powers, or 2 types of engines. You have the flood net and the flood hosts. One focusing on the network and one focusing on the individual host. All right, let's jump off the metadata, and I'm going to jump into the flood engines. You can see that we have our flood host and flood net. The flood host focuses on the individual signatures that attack a specific host. ICMP floods, Smurf attack, UDP floods. And the reason that you don't see TCP in that list is it's very difficult to attack a single host with TCP, since well, it's possible, but really it's much easier to just flood with UDP because the host has to examine each of those. Whereas TCP it's a session based. It doesn't just take one packet at a time. ICMP and UDP do, which is why you see those under the host. If you jump it over to the network, that's where you see the net floods coming in with UDP and TCP. You'll also see the ICMP attacks, and it lets you get more granular with replies, requests, or any ICMP messages. As of right now, you can see none of them are enabled. It's because these are prone to false alerts. If you have, a day where just traffic's above normal, it could trigger this alert. As a matter of fact, let me edit the TCP one and show that to you. You can see underneath here, I'm looking at the TCP. I'm going to scroll down a little bit. The engine is the flood net. And you can see the event action is just to produce an alert. And here's our tunable parameters. The gap, peaks, and rate. Now, you notice if you hold your mouse over any one of these, it gives you a brief description of them. Now, the peaks is just the number of seconds that the traffic has to be above the normal rate in order for this signature to trigger. Now, I guess it may make sense to talk about this rate. What is this? This is in packets per second, the number of packets that should pass per second on average. This is your normal rate. So you can type in there what you would perceive to be the norm for the network. Now, it's at 0 right now. You might think, well, that means it's just disabled, right? Well, no, it's actually even better than that. 0 means that you have put the signature into diagnostic mode. It's going to watch your network and establish its own average rate. Isn't that good? I mean, it's going to watch what's going on instead of you just picking an arbitrary number off of the head and say, it should be below this. It will watch and establish a normal rate. Then the peak and gap come into play, where the peak says if it goes above the normal rate for 3 seconds, fire the signature. And the gap says I will reset the signature once it has been 3 seconds below that normal rate. Does that make sense? So peak is going above. The gap is the below. It's saying I'm going to keep this signature fired until we go below the normal rate for, as of right now, it's 3 seconds. So that allows you to really see what's going on as this signature is watching the network for being flooded. On to the next engine. It's the Normalizer engine. This engine discovers packets that are not normal, as the name implies. And I guess if I were to expand on that, I would say and makes them normal. The main thing that this focuses on, you can see there's 2 inspection types, 2 engines, the TCP normalizer and IP normalizer. If I were to focus on the main topic of the normalizer, it's fragmentation. One of the ways to escape detection and to get by access lists, to get by a lot of things, is to fragment your packet into a bunch of different pieces. So by fragmenting it, a lot of the devices that inspect will just say, hey, either there's too many fragments to put them all together and inspect them, or I just don't inspect fragmented packets. Now, it's not something that you can just deny. I mean, fragmentation happens as you send packets over the network. But what the normalizer does is it reassembles those fragments. As they come into the sensor, it's going to take all the individual fragments, put them all together, look at the packet, make sure it's normal, then fragment it out and send it on its way. So it looks like nothing ever happened to the packet, but it was really reassembled along the way. It also will do things like looking at the checksum, making sure that the checksum's okay. And if the checksum's off, it will fix it. And it's kind of interesting because that's a known attack, is to put a checksum on there that's bad and flood with bad packets. Well, the normalizer makes it normal. It actually will detect problems and fix them. So back over on the IPS sensor, if we were to change our engine over to, there it is, the normalizer, you can see it's going to populate this with just all of these normalizer signatures that allow it to inspect and normalize the packets. And look at the theme: fragmentation, fragment, 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 fragment. It's fragments the whole way down, trying to, and most of them are enabled to not only grab those packets, but notice a lot of these are beyond just the alert. It will also deny the connection if the fragment flags are considered invalid. And as you go down, you can see some of these also deal with the TCP session packets. Remember, I said there was the IP normalizer and the TCP normalizer, dealing with normalizing all the different TCP options and TCP settings that come into our network traffic. Well, let's draw the line in the sand at that point and take a good breather between the two-part series of the signature engines. Just to hit the high points of what we've discussed, we talked about the need of a signature engine, what the signature engines are, and their purpose. And remember, these engines are really all the services that run on your IPS sensor that manage their own individual set of signatures. We then got into the individual signature engines, and in this nugget, we started talking about the atomic signature, where we were looking at a single match packet, the flood, where we're looking at denial of service attacks and watching those come through, making sure that a specific host or specific network is not flooded with data. We talked about the meta engine, which is one of my favorites just because it's a compilation of multiple signature matches. It sees events that occur and puts the pieces together. It's like the Sherlock Holmes engine. When it sees the vase fall on the floor and crash and the hole in the window, we take into mind, hey, this might not be two random events. There may be a sniper outside that just shot the vase on the wall or something like that. It puts the pieces together. The normalizer engine, the one that allows you to inspect traffic that is fragmented or not normal, go through, put it all back together, aka fix it, look at the packet as a whole, then fragment it again and send it on its way. In part 2 of this series, we'll start looking at the rest of these engines and discussing those individually. I hope this has been informative for you, and I'd like to thank you for viewing.